Mm, Hello, Professor. This video is recorded to explain the implementation of our project. This is the repository that we are working on. Um, we have a README here to explain the project structures and basically give a short descriptions of what each file does. Our project contains four main components. The first one is the grid map implementation. This component is responsible for converting an image to a map. An image is divided into small cells of, and each cell contains a grid size pixels in it. And the second part is the A-star algorithm. The implementation of A-star is located in the folder A-star. We follow the dynamic weights from this paper, and the genetic algorithm implementation is in the genetic folder. We have the A and colony algorithm to generate the initial population, and we follow this paper, the first part of this paper. And also we have a function to calculate the path value, the smooth value, and on the operations of genetic algorithm, including selection, crossover, mutation, insertion, and two additional mutation and two additional operations introduced in the paper, mobile this paper, including insertion and deletion. And the smart path smoothing is used for A-star algorithm to make to improve the path found by A-star algorithm, and it is in the folder path smoothing. For our project, we also created several notebooks to experiment with different maps that we mentioned in the report. However, for the purpose of demonstrate how we conduct experiment, I will just go through the simplest map. The original image is of size 440 times 580 pixels. The map is constructed, and the original image is divided into small cells of size 10 by 10 pixels. So the image is divided into 59 columns and 45 rows. The starting point is at the origin, and the goal state is at the bottom right of the map. We also have some function to check whether the map, whether the starting point and the goal point line in the obstacle space. First, I will run the A-star with Euclidean heuristic. We measure the execution time, and also we count the number of turns. We have the function to count the number of turns of a path here. Basically, we will just calculate the angles between 3 points along the path and compare it with 179 degrees. And the path length is simply the sum of Euclidean distance between points on the path. So I start search for this map. It returns a path of 79, the path of with length 79 and 5 turns. And for the proposed heuristic with dynamic weight, as you can see, the path return is identical to the previous one. The proposed heuristic in the paper here is not either the Euclidean heuristic or Manhattan distance. It is the between of the two heuristics. And we also apply dynamic weight A star search. A weight is applied to the heuristic function. Alpha is the ratio between the distance from the current node to the goal node divided by d. D remains a constant because it is the Euclidean distance between the starting point and ending point. So as the search process, during the search process, if the current node is become close to the goal state, alpha, the value of alpha here will be decreased, and the influence of the heuristic value will be less on the evaluation function. As you can see, the number of rich nodes of the proposed heuristic with dynamic weights is less than the rich node using the traditional heuristic, Euclidean heuristic. However, the path is identical. And we also follow the smoothing process. We basically we apply the smoothing process on the path found by the dynamic weight A star search. And you can see we can further improve the path length, and also the path quality is also increased because the robot does not need to turn unnaturally comparing to the previous path. For the implementation of smoothness, for each point along the path, we will try to find the possible next turn by connecting the starting the currently considered point with each consecutive points along the path. If there is a line, if the line connecting them pass through any obstacle, indicates that it is a necessary turn so that the previous node cannot be skipped. However, if there is no obstacle, we can skip the current node and consider the next point. Our project also implement the genetic algorithm. So the genetic algorithm take the math as a parameter, and also we can specify the number of generations and the number of ants for the ant colony algorithm to generate the initial populations. And we also can has some settings on the fitness function. We can set the importance of weight length and weight smoothness. So I will explain the fitness function. For the fitness function, it is minus the path value. Path value here is the sum of heuristic function, the sum of Euclidean distance, and the smooth value here is the sum of turning angles of the path of each individual, because each individual in the population is a possible solution to the problems. So basically for each population we will consider the turning angles along the path along the path. So if the angles is less than 90 degrees, which means that this turn is unnatural, so the smoothness, we will apply a penalty to the smooth value. If it is 90 degrees, it's good enough. However, if it is greater than 90 degrees, means that this robot needs to turn slightly, so smaller penalty will be applied to the smooth value. Okay. So we finished the algorithm finished the execution. As you can see, the time here is a lot longer than the previous algorithms. The path length is also a lot bigger than the previous one. However, the path return is surprisingly reasonable, because as you can see from the previous path found by A star, it seems like that the robot will likely to collide with the obstacle here, and here, because the A star heuristic will likely to prefer the diagonal line. So for the genetic algorithm, because the smoothness value is taken into account, the turning angles is taken into the fitness function, so eventually it will return a path simple like this one. Although the path length is higher, however, this path, if the robot follow this path, it will have lower possibility that it will collide with the obstacles. Here is the path found by each generation, the best path found by each generation. As you can see, the number of turn is reduced through each generations. The last generation contains only one turn. And I will plot the fitness function here, the fitness values and path value and smooth value of each generation. As you can see, the fitness value of the genetic algorithm increase through every generations. Through after each generation, the turning angles is decreased, and also the path length is also decreased. Um, for the next part, I will explain how genetic algorithm works. I will pick the first path, the best path from the first generation, and the last path from the generation, and then I will calculate the fitness value of the two paths. As you can see, the first path is shorter than the second path. However, the first path is have many turning angles, therefore the smoothness value of it is higher than the second path. Because the fitness values calculation, for calculation of fitness value, we place higher weight for smooth value. Is it the setting when we run the genetic algorithm here? So therefore, eventually the fitness value for the second path is higher than the first path. So this is the idea of selection based on fitness value. Therefore, we can set the weights of smooth values and path values based on different purposes depends on the maps. And the next operation is the crossover. Let's consider the following two paths. For the selection crossover, we will try to find a common grid along the two paths and perform single point crossover at that common grid. As you can see, from the common points, the orange path will follow the path that previously belonged to the purple path. Here, notice that I also set the P crossover probability of crossover equal to 1 to make sure that the crossover operation is performed. And the same for mutation. For demonstration, I also set the P mutation equal to 1. As you can see, one point along the path is mutated by selecting one of its available surrounding grids. And also, this is the insertion operations. It will add some points to an individual in order to make the continuity of the path. And finally, we perform the deletions. And as you can see now, the path become a lot shorter and smoother than the original path. Here you see the path before on operations, and this is the resulting path. Final part for our project is the UI, so that we can experiment with different map or generate a random map. For example, let's generate a random map here. A user can pick the starting point and also the goal node, and apply different search algorithm, and the report of rich nodes and elapsed time is also available to the user. And for the heuristic function, user can set the number of generations and the number of ends to generate the initial populations, the crossover of probability, and the mutation probability. The genetic algorithm. This is the report for genetic algorithm and the path for the genetic found.